So I want to begin this part 2 video by reviewing something that we finished the first video with, and that is division by a unit fraction. So in this case we're dividing 3 by a half and we get 6. And the effect of dividing by a half is the same as multiplying by 2. So if we have n equal parts, so if our fraction says 1 over n, so that's a unit fraction, so n is telling us how many equal parts the whole, one whole, has been divided into. It seems reasonable and correct that in order to determine the number of those parts, we would take the number of pieces that the whole has been divided into and multiply by the number of wholes. So that explains why we're multiplying by the denominator, because the denominator is the number of parts in one whole. Okay? So let's see if this generalization will translate into multiplication of a fraction by a unit fraction. So let's clear this. And we're going to set up this question right here. 5/6 divided by 1/3. And let's think of it as how many times can 1/3 go into 5/6. And you may want to pause the video for a moment to kind of work this out and build a model for yourself. I'm going to go ahead and work on it. So here's my whole. I'm working with fractions, so I need to know what the whole is about. And so I'm going to grab 5/6, which is right here. So if that green bar is 1 whole, then the yellow is 5/6. And my question is, how many times can 1/3 go into it? So 1/3 would fit into it once, twice, but not 3 times. So we can see that half of the final third, of the third, is fitting into 5/6. So I would say that my answer to this question is 2.5, because 2.5 go into the yellow 5/6 bar. Now let's see if the generalization we have from the 3 divided by half question works here. So what we would do then is we would say, okay, well, what if I took 5/6 and I multiplied by 3? Now we understand 3 to be 3 wholes, so 3 over 1. So again, I am multiplying by 3 because the whole has been divided into 3 equal parts right here, right? And 3 of them go into 1 whole, but how many will go into 5/6? If I do the multiplication, I get 15 for my numerator, I get 6 for my denominator, and if I simplify that, I'm going to divide each of these by 3 to get 5 halves, which does turn into 2.5. So this actually works when we're multiplying fractions times fractions. And what's more, we actually have a reason why it works. So let's talk about this invert and multiply algorithm. Ann Conjander says that this procedure will work with any fraction division, but that it should be seen as a last resort when other options don't work out, either modeling or visualizing, or another algorithm that we haven't talked about yet, the dividing numerators algorithm. When those don't work out simply, then invert and multiply is the one to go to. So let's consider this, and if I am dividing a question, I'm doing a question like this one here, 1/6 divided by 2/3. So the question becomes, how much of 2/3 will go into 1/6? And if I model it over here, there's my 1/6. How much of my 2/3 will go into it? And you can probably see visually or you otherwise know, that 2/3 will break down into 4/6. So 4 parts. One of those parts will go into 1/6. So the answer is going to be 1/4. But how do we do this with invert and multiply? Okay, so there are three conceptual ideas used to develop this procedure. First of all, just as I can, if I'm doing division by 20, 100 divided by 20, I could split that 20 into 10 and 2, and I can divide 100 by 10 and then divide the quotient by 2 and get the same answer. I'm going to do the same thing here. So I'm going to divide 1/6 by 1/3 times 2. So I've broken 2/3 into 1/3 times 2. Okay? And that's within brackets, so when I take away the brackets, I'm going to be dividing 1/6 by 1/3 and then dividing again by 2. Okay? Now, remember that division by a unit fraction, in this case 1/3, if I'm dividing by 1/3, it is equal to multiplication by 3 because the whole is divided into 3 equal parts. So I need to take the number of wholes, in this case 1/6, and multiply that by the 3 equal parts that the whole is divided into. And I still have my division by 2. And I'm going to finish it up here. So the third concept is the converse of the second one. If dividing by 1/3 is equal to multiplication by 3, then the opposite must be true. So in the case of division by 2, if dividing by 2 must be equal to multiplication by 1/2. Okay? And now I can simply take these two parts, these two factors, and put them together. So I still have my 1/6, but this time I'm multiplying it by 3 halves. Et voila, my division has become multiplication. My divisor has now become its reciprocal, and I am multiplying, but I know why this works. And I can finish my question by doing the multiplication, and that equals 1/4. So this is how it works. Students need to see this and understand how this algorithm works instead of following it blindly. If they know the mechanisms and the concepts behind the algorithm, they will understand it, and they're less likely to forget it. They will use it correctly in the future. All that being said, let's remember that Ann Kajander tells us that the invert and multiply algorithm should be our last resort. When we're dividing fractions, we should first be using modeling or visualization. But there's another algorithm that may be useful in some situations called the common denominator algorithm, or by others, dividing numerators. And let me show you what I mean. If I have this question, 3/4 divided by 1/4, I can use invert and multiply, but I don't have to. There's a simpler way to think about it. Okay, my denominators are the same, so let's take a look here at what it looks like. So my whole is right there. I'm aware of the whole because that's important with fractions. I've got my 3/4 out. Now the question is, how many times will 1/4 go into 3/4? And it should be fairly obvious that 3/4 will fit into 3/4, right? Okay, so what am I doing here really is I'm dividing the numerators. I don't, in this situation, I don't really need to worry about the 4s. The reasoning for this is similar to 3 divided by 1. Okay, so let's take a look at a different example. we'll clear this. An example where we don't have common denominators already. So 2/3 divided by 2/12. Now this one's going to be a bit more difficult to model because it's not easy for me to get 12ths on this app. So I'm just going to put this down. I'm going to change this back to basic, which means I'm going to lose my question. It's not the last time that will ever happen. And let's write it down again. 2/3 divided by 2/12. Okay, well, let's take this out. Now I know that if I want 12 units, I want this and this. So I'm going to stretch this out, put the marker down, get rid of that red. I'm going to stretch this out. So that is 12 units long. So now I can get rid of these. So 2/3 of 12, I believe these are thirds. Yeah, those are thirds. So what would be 2/3? Brown. Okay, so the brown one is my 2/3. Okay, now 2/12 in this event would be this. That is 2/12. Now, how many times will that go into the 2/12 right here? How many times will that fit into the 2/3, which is the brown bar? Well, I think we can see, and I'm going to just use a red one to model, once, twice, thrice, 4 times. It's going to happen 4 times. Okay? Now let's take a look at what happens here if I use the common denominator algorithm. So I need to change my 2/3, and I'm going to change it into 12ths. So that's going to be 8/12 into divided by 2/12. So what this is saying is now I'm changing my 2/3. I'm going to change it into 8/12. So there are my 12s coming down. There are 8 of them, or there will be 8 of them by the time I'm done. So how many times will this group of 2, which is circled here in red, fit into this group of 8/12s down below it? Once, twice, 3 times, 4 times. The answer is going to be 4. Now let's take a look at what's happening with the numbers. My denominators are the same. I'm dealing with the same units, so I just need to figure out how many times 2 of those units will fit into 8 of those units. So the thinking is similar simply to 8 divided by 2. So in some situations, this is conceptually a lot more accessible for students, and that's why Ann Conjander says that this should be something to attempt before invert and multiply. So showing students several different ways to divide, leading them to those algorithms, just gives them more to work with and greater chances of success. In my multiplication videos, I mentioned that one of the misconceptions was that students grow up learning whole number multiplication and believing that multiplication always makes things bigger, that the product should be bigger than either of the factors. The reverse tends to be true for division. When students do whole number division, and they do it for years before they get to fractional division, they're used to the quotient being less than the dividend. And we've seen cases already where that's not true with fractions. So they need to understand exactly what is going on and why it's happening so that they don't get caught in that misconception where they might do a question like the one we had before. We had 1/6 divided by 2/3, and the answer was 1/4. A student may recognize that 1/4 is a bigger number than 1/6, and may not accept that as a correct answer because they're used to having a bigger dividend than a quotient. So it's very important to use these representations and to use these concepts and to make sure that kids understand them so that they won't fall victim to those misconceptions. So that is the end of the video, dividing fractions, part 2. Hope you've found something in here that'll be useful in your practice. Thank you.